So today we're going to talk about vector spans in section 2.2. So I want you to go ahead and get section 2.2 open so you can see it, and you'll want to have MATLAB out so you can practice these skills. Okay, so first of all, a span, what is a vector span? Okay, so the span of a set of vectors is the set of all possible linear combinations of that set of vectors. All right, and then we're going to ask the question, how do we determine if a vector is in the span of a set of vectors? Well, it turns out we can row reduce, right? It turns out that if we set this up correctly, it's the same situation as solving a set of linear equations. So we will have the coefficient matrix, those will be the vectors, and we'll have a vector to check. Well, that's like the solution vector. Okay, so this is how it's going to go. So in example one, the set of vectors is vector v sub 1, vector v sub 2, vector v sub 3, and we're checking to see if the vector b is in that span. Okay, and again, this matches the notes. So here's the process. Here's how it goes. We're going to create a matrix A whose columns are v1, v sub 1, vector v sub 1, vector v sub 2, vector v sub 3. Then it turns out we can create the augmented matrix A comma B vector B. Okay, I'll show you how to do all this in just a second. And we can row reduce that augmented matrix to RREF. As a matter of fact, that's a command in MATLAB. So we've got a real quick way to do step 3, and then step 4 is going to introduce the rats function, and it's not as disgusting as it sounds. Rats is short for rationals. In other words, instead of having decimal approximations to numbers, it's going to put them in rational form or fraction form as often as it can. Okay, so let's jump to MATLAB and see how that goes. So again, we're looking at section 2.2, right? And we're doing this example 1. And I've just copied this. So remember, if you hover over the top right corner, you can just copy that. And so I've put some semicolons in here to suppress the output, but that's what this first section is doing right here. Okay, is just entering the vector v sub 1, the vector v sub 2, the vector v3, and the vector b. And so we're supposed to see if b is in this set of vectors. Okay, well first let's create the matrix A. All right, so what we're going to do is we're going to say A equals, and then we're going to do square brackets, v1, comma, v2, comma, v3. What's that going to do? It's going to take these column vectors. They're going to be the 3 columns of a 3 by 3 matrix A. Check that out. And if you want to look, the 5, 3, negative 2, that is in fact the correct vector here for v1. v2 is 0, 2, 5. And you can see our middle column is 0, 2, 5, then 3, 4, 3. So we've got the right vectors. The vector b is 4, 0, 2, right? And we have the vector 4, 0, 2. All right, so just to show that, so we see that we've got everything in there the way we want it. Okay, now let's check this out. Here's another trick, and let me get a little more space in here. All right, so that example 2 isn't cluttering up what we're thinking about. Watch this. I can do A comma B, right? So it's going to go and grab this column vector B, and it's going to augment it with A. And there you go. So you see we still have the exact same situation. The first 3 rows, the first 3 columns of A are vectors V1, V2, and V3. And now the 4th column of A is the vector B. So we're asking, is B in the span of the set of vectors? Well, think about what this means. When we row reduce this matrix here, what are we doing? Right, we're trying to find a linear combination of these vectors that's equal to 4, 0, 2, right? It really is looking to see if there's a linear combination. So if there's a solution to this augmented matrix, we are golden, right? We know if there's a solution to this augmented matrix, that and whatever linear system of equations that it represents, we know if there's a solution, then yes, B is in the span of vectors. If there's no solution, then B is not in the span. Okay, so what are we going to do? We're just going to use REF form. And I'm going to use this augmented matrix. The computer knows what A is, and the computer knows what B is. So we're going to do RREF of A comma B. And notice what it does. Okay, so it says that x sub 1 is about 5.23 and x sub 2 is about, so this is the linear combination. The weights are given here, right? And the vectors, this is x sub 1 and we've got x sub 2 and we've got x sub 3, right? So now this solution does in fact give us the correct linear combination of the vectors that produces 402. Okay, so because there is a solution, right, this is a consistent, we reduced it to RREF, and this is consistent, right? This matrix here is consistent. It has a solution, therefore the matrix, excuse me, the vector B is in the span of the vectors. All right, and let's talk about this RATS function because this does look a little bit ugly. And let me leave it. Let me scroll up so we can see. Wait, sorry. If I can scroll up just a bit so we can see. So this is what AB is equal to RREF of AB. Let's do this. Let's do RATS of RREF AB. So all we're doing is we're wrapping the RREF of A comma B into the RATS function. Okay, so RATS is going on the outside. So RATS is going to rationalize the output. And here we go. All right, so you can see, let me scroll down just a little bit, right? You can see that we have a fraction 68 over 13, we have 90 over 13, and we have negative 96 over 13. So yeah, those 13 fractions are not, we're not having good luck with these decimal approximations. They don't look like, fractions we know, like 7.25 or 7.4. They're not simple decimal numbers that we can easily see what the rational number is. But we can use the RATS function and we can see better what's going on. So example 2 is very similar. All right, we have a set of vectors v1 and v2, and we have a vector b, and we're trying to see is there some linear combination of v1 and v2 that is equal to b. We're trying to see if b is in the span of v1 and v2. And let me get rid of the ink. And oops, sorry, there we go. And just to let you know that the same solution path as before will work. Okay, so let's get back into MATLAB. All right. And so I have the whole problem shown right here. And again, these values come from example 2. Okay. All right. So, you can just, copy right here and get V1 and V2, which is what I've done. And here we have V1, V2, and B. And again, the output is suppressed. I'm going to create the matrix M to be V1 comma V2, and let's see what that gives us. Okay, so we have 0, 4, 0, 4, and negative 1, 5, 0, and negative 1, which, as you can see, is exactly what we're supposed to have. All right. And then what are we looking to do next? Remember, we're going to do RREF of the augmented matrix M and B, but let's just look at M and B first. So we have a 4x3 matrix, and notice that we have all zeros in row 3. So the very first thing we're going to do is we're going to move all the row of zeros to the bottom. So we're going to expect this to be a 4x3 matrix with all zeros. The row on the bottom will be all zeros when we get it to RREF. So let's do RREF of this M comma B augmented matrix, M comma B. And again, you don't need spaces. I put the spaces in just because it makes it easier for me to see. I kind of like it like this, where I can see what's in there. And I do RREF. And this looks nice if you ignore the bottom row, but we've got to remember, right, that the third column is our vector B. That's supposed to be our solutions. And what is this saying? Well, this is fine. It says that x sub 1 is equal to 0 and x sub 2 is equal to 0, but this says that x sub 1 plus x sub 2, both of which are 0, equals 1, right? So we end up, this third row is actually an equation that says 0 equals 1, which is not correct, right? Right? So the biggest problem here is that the row reduced form, even though it looks nice, even though it looks like 1, 1, 1 down the main diagonal, you got to remember that there's actually the augmentation line is right in here. And so this third row is actually illegal, right? It's saying that 0 equals 1, which cannot in fact ever be true. All right, so let's get rid of that ink and jump back into the presentation file, okay? And again, this is why I said something turns out to be very different, right? So the answer here is no. No. Why? Because in RREF form, we row reduced to a point where we showed that that linear system of equations was inconsistent. Therefore, it has no solutions, 0 solutions. So there are 0 linear combinations of V1 and V2 that equal B, the vector B. All right, so what are we trying to get across here? Let's look at the key takeaways. So how do I determine if a vector is in the span of a set of vectors? Okay, I take the set of vectors and I turn it into a coefficient matrix by making each vector a column of a matrix, right? So if I have a set of 4 vectors, then I'm going to have 4 columns in my matrix. If I have a set of 6 vectors, I'm going to have 6 columns, okay? And in MATLAB, I'm going to go ahead and create that coefficient matrix. And then I'm going to augment that coefficient matrix with whatever vector t that I'm checking to see whether or not it's in the span of the set of vectors, right? So the set of vectors are the columns of M, and then I did D and T here. Sorry, this should be an M. I'm sorry about that. So I create the augmented matrix M comma T to check to see if the vector T is in fact in the matrix M, okay? Sorry about that. Let me ditch the ink. And RREF is great if we're just checking to see if the linear system of equations is consistent or inconsistent. We can use RREF and we can tell really quickly, okay? But I want to warn you, don't just start using RREF. We still need to know how to row reduce. Okay, there will be row reducing on the quizzes and tests, and you'll have to do it. And even sometimes you'll have to do it by hand. Okay. And then the RATS functions. This is the new one. So it turns out that we can actually solve for this using stuff we've already learned. Okay. The new thing we learned was the RATS function, and it's not just RREF that it'll work on. We can do this when we're going through our row operations. And if we get something ugly in our row operations, we can actually do RATS of the row operation, and it'll do the same thing. It will do all the calculations as rational numbers, and we'll be able to see the fractional form rather than the decimal form. Okay, so a pretty easy section with some really cool stuff. And again, probably the coolest thing I think is this RATS function. I'll be back for section 2.3. Have a great day, everybody.